This is video number 2 for section 5.5, medium case where A is given but B is not. Just another example of the same kind of problem. We're going to create a model and then we will use the model to answer a question. This one's going to be just a little bit more difficult than the last one in terms of creating the model. This is one of those half-life problems. You can take a look at the problem here. This one concerns caffeine in your body. It says the half-life is 6 hours. Remember, half-life means the time it takes for half of the substance to disintegrate or decay. So we got this guy Stuart. It's 9 a.m. Monday. He drinks a cup of coffee. We're trying to figure out when there's going to be only 0.5% of the caffeine left in his bloodstream, so a little less than 1%. First step, we got to fill in our let statement here. In a half-life problem, it's very normal for the y variable to stand for the percentage. So P here will stand for the percent of caffeine in his bloodstream. T, so often we use years, but you can tell in this problem that our unit of time is hours, so we'll say T hours since the start. He drank it at 9 a.m. on Monday, and so we will start there as well. Let's go ahead and try to create a table for the function. You might remember these half-life problems generally all start the same way. P is the percentage of caffeine in his body. Well, at the start, in other words, when T is 0, all the caffeine is there, so that would be 100%. And then if the half-life is 6 hours, that means if I go forward 6 hours in time, now there's only 50% left, half of what was there before. And if I go another 6 hours, half of this, in other words, now I'm at 25% that would be left, and so on. And if I wanted to, I could fill out this table further. The table is helpful for two reasons. Number one, it confirms what kind of function we are looking at. It is clearly an exponential function because I can see that to move down the table here, I just go times a half, times a half, times a half. So it is definitely exponential. Half-life problems are always exponential functions. And now we want to go ahead and write the equation. This is just slightly more difficult than the last example because we were not handed the b. I can see the a, the y-intercept. It's here right in my table. 0, comma, whatever is always the y-intercept, so that's easy. The a is definitely 100. It's tempting to want to say that the b is 1/2 because I do times by 1/2 as I go down here, but the problem is the x's, or in this case the t's, are not going up by 1. So I do not know the b. I'm going to have to figure it out. Our method for the medium case was take the exponential model, fill in the piece that you do know, namely the a, and then use the temporary plug-in idea where you pick one of the other points in your table. You temporarily plug in the x and y values, the input and output values, so 50 for the output and 6 for the input. And then you solve for b, the only letter left. That'll take just a couple of steps to do. I'll need to divide both sides by 100. And I can go ahead and reduce that other side to 1/2. I'm almost done. To get b by itself, this is a power equation, and we've been using the words reciprocal power. Take each side to the reciprocal power, so raise each side to the 1/6. And then I just need to grab the calculator and type that in. I don't have any rounding instructions here. I just went to 4 decimal places. It's always a good idea to keep your b out extra long. And I got b is about 0.8909. I have all the information I need now to write the equation of the model. Let's use the right letters. The y variable was p, and then I have a, which is 100, times b 0.8909 to the t is my x variable in this problem. So here's the model. Everything we've done so far, we've done before. That was all review. Part D is where we get into the new stuff. Remember, the original question said, when is this caffeine going to be down to just 0.5%, less than 1% left in his bloodstream? Well, this is very similar to what we did in the last video. I can either plug in a percent or I can plug in a time. I'm being asked here to plug in a percent and find the time. The question is to find the t. So I take my 0.5 and I replace the p with 0.5. And here's what I have. Now I know you might have been tempted to change this 0.5 to a decimal to move the decimal point a couple places to the left. That would be incorrect. Remember, in our let statement, p stands for the percent. It doesn't stand for a decimal or a fraction. It is a percent. The numbers in our p column are percentages, 50%, 25%. So if you want to talk about 0.5%, then your p is 0.5. The rest of this is really identical to what we did before. As soon as I see the t in the exponent position, I think to myself, well, I'm never going to get it out unless I go to logs. And so that's what I do. I can't do that yet because I have this junk here in the front, this 100 that's being multiplied. You have to isolate that base and power. You have to put it in exponential form. So do that first. This would come out nice. You can either divide it or you could just leave it. It doesn't really matter. I just went ahead and left it. I know in the end I'm just going to type it into the calculator anyway. Now I am in exponential form, so I can log each side. I'm logging this whole thing, and I'm logging this whole thing here. I'm doing that only for one reason, so that I can use that great rule of logs. It's unique to logs, that rule about moving this guy to the front. Let's go ahead and write that out. Each log here represents an exponent. I could go to the calculator and figure out what those exponents are. I just don't want to do that because I don't want to round in the middle of the problem. So I'm just going to leave it. In order to get t by itself, just divide both sides by this log on the right side, and we're all set. On the right, I've got the t by itself, and on the left, I just have this messy thing that I can type directly into the calculator. Remember, don't do anything goofy like try to cancel the LOGs. LOG is not a number, it's an operation. This is some exponent up here, and I need to divide it by this exponent down here. Just type it all into the calculator, and let's see what we get. Rounded to the nearest hour, I got t to be about 46. So we're saying about 46 hours later is when he's finally down to less than 1%, to that 0.5%. Now we're supposed to give an actual day and time, so we're going to have to think about that for a minute. He drank the coffee 9 a.m. Monday morning. Let's see, 46 hours later, that's almost 48 hours later. 48 hours later would be 9 a.m. Wednesday morning. So if I just back up 2 hours from that, I think I'm ending up 7 a.m. Wednesday morning. That would be the final answer to the problem. Again, you just need to practice this process over and over and over. It is thankfully very much the same each time. You just have to make sure that you understand the steps and that you can demonstrate them.